Hi, I'm Bob Caporale, Assistant Product Manager for Pirelli Cables here in Columbia, South Carolina. Today we're going to talk a little bit about cable basics. Basically going to step through the construction of a medium and low voltage cable. We're going to focus mainly on medium voltage cables and try and understand some of the basic concepts that go into the design of these. Let's start off with just a basic conductor. If we put this overhead in air, like we would see on a normal distribution line hanging on a wood pole, what you would have is air being the insulator. So the voltage won't jump to ground as long as you maintain a certain spacing between that conductor and any ground plane or any other phase. And the higher the voltage that you have, the more spacing that you have to have, therefore the more air, and the less chance of drawing an arc. That works well as long as you have the cables in air, but as soon as you have to put those cables underground, of course now you have the cables laying on a ground plane and you have to insulate it somehow. So we do that by extruding some type of a dielectric or insulating material over the conductor to keep it from shorting to ground. There are many different types of materials that you can use for this purpose. Most materials, when you heat them up to high temperatures, will melt. These are called thermoplastic materials. And when they're melted, they turn from a solid state to a liquid state. And when they're cooled, they turn back to a solid state. And they form whatever shape they were in when they were last a liquid. This, of course, if you have high temperatures, is a problem, especially in cable insulating materials. So in order to prevent this from happening, what we use is what's called thermoset materials. And those thermoset materials, also called cross-linked materials or vulcanized materials, those terms are interchangeable. The properties of those are that you can heat those to high temperatures and they won't melt. They can have some deformation, but the point is they won't melt off of the cable. So this makes it ideal for applications where you have high heat, such as a power cable where you're drawing current which will generate high heat. In order to change a material from a thermoplastic state to a thermoset state, you have to introduce some cross-linking agent. There are various types of materials that you can use for that. One of the most common is peroxide, which is used very commonly in medium voltage cables. And peroxide is introduced, and you cure it under high heat and high pressure. And you have a cross-linking process, which in turn will give you a material that cannot be melted. Another way to cross-link a material is to introduce a compound called silane into the process. And you cure this using moisture. This is used commonly in low voltage materials and achieves the same effect. Now in a medium voltage cable, if you put a dielectric material directly over the conductor, you have some problems. And the reason you have problems is because you have a fairly high voltage stress. On low voltage cables where the stresses are not that high, you can extrude a dielectric material directly over the conductor and pretty much have no problem. You've achieved the purpose of keeping the voltage from shorting to ground, and that's the end of it. You increase the insulation thickness on low voltage cables mainly for mechanical purposes, but it takes very little insulation and is very low stress. When you get into medium voltage cable design, you have a whole new realm of problems to deal with. One of those problems is a phenomenon called corona discharge. Anytime you have a potential difference between a void anywhere in the insulating material, what you're going to do is draw an arc across that air gap. The air in that air gap will become ionized. And this causes degradation of the insulating material on either side. And over time, this will cause a cable failure. So anywhere where you have a potential to have a void in that system, you want to try and avoid it. So one of the ways that you do that, knowing that when you extrude a dielectric material over the conductor, you will not be able to extrude it so that all of the insulating material is in constant contact with the conductor. So you will have gaps. So one of the ways that we avoid having those gaps and having the phenomenon of corona discharge at that very crucial interface is to put a semiconducting conductor shield and extrude it over the conductor so you're filling in all of those voids with an air gap and creating a nice smooth interface. One of the other reasons why you have a conductor shield at this interface is because where there's a high point in the conductor and a low point, you're going to have an asymmetrical distribution of your voltage stress within the cable insulating material. Again, this will be a problem. Let's talk a little bit about the actual dielectric material that you would use in the design of a medium voltage cable. Again, this is a different material than a low voltage cable because you have a different set of concerns once you have the higher voltage stresses. One of the problems commonly referred to as treeing in a medium voltage insulation system refers to degradation in the dielectric that's due to high voltage stresses or higher voltage stresses than you would see in a low voltage cable, and usually moisture or some type of a contaminant within the insulating material. Now we've heard some funny stories about what people think a tree retardant cable actually is. We've even heard some people say that a tree retardant cable is a cable that actually withstands the growth of roots going through the insulating material. That's just not true, so make sure you don't go to the field with that one. What we want to get across is that a cable tree or a water tree is referred to as a degradation of the insulation due to voltage stress and water inside the insulating material. There are two different types of trees that are commonly referred to. One is called the bow tie tree, which usually starts somewhere in the insulating material itself and is usually initiated from some type of a contaminant or something in the extrusion process that just wasn't right. We'd like to have an ideal extrusion process with medium voltage cables, but unfortunately that's not always the case. Bow tie trees in and of themselves are not huge problems as long as they're fairly small and there's not a high density of them. However, if they get very large and there are a lot of them, it can be a problem over time. The ones we really have to watch out for, though, are vented trees. And vented trees usually start at the conductor shield or the insulation shield interface and are usually caused by water migrating into the insulation system. That, with the combination of voltage stress, again, will cause a degradation of the insulation, which, as you degrade the insulation over that time, you really have kind of like a hairline crack, and you have a very high stress. As the tree grows, you increase the stress more and more, and you usually increase it to points where the insulating material can't stand that high of a stress and it breaks down or fails. So long story short, you want to try and keep trees from growing within the insulating material. So how do we prevent trees from growing? Well, there are many ways. Because trees can grow from, like I said, contaminants or voids within the extrusion process, one of the things that you want to do is maintain extra clean materials with as few contaminants as possible, and also maintain cleanliness throughout the extrusion process to try and get the extrusion process as clean and as controlled as possible. Another way to prevent trees from forming within insulation materials is to keep the water out of the cable, plain and simple. One of the ways we do that is by using a strand filling material at the conductor. By filling the strands of the conductor, you ensure that water will not get in during manufacture, during cable handling, while the reels are outside. The point is that if you fill those voids in the conductor, you won't have water there. And with water not being in the conductor, it can't get into the insulation from that interface. Another place where you can block the water, of course, is from the insulation shield. Pirelli does this using water-soluble powder, in some cases water-soluble tape. In the case of the triple seal, we use a sealed LC shield with water-soluble agents below and above it. Another way to prevent trees from occurring is to use the proper insulating material for the proper applications. The two most common medium voltage insulating systems are XLP or EPR. XLP comprises of a family of standard cross-linked polyethylene or tree-retardant cross-linked polyethylene. Both of these have similar properties. The difference is that with cross-linked polyethylene, trees will grow very rapidly. This causes those cables to break down in very few number of years and has caused problems in the past. Tree-retardant cross-linked polyethylene, on the other hand, starts with the same base material as cross-linked polyethylene. However, there's a tree-retardant additive that's incorporated into the formulation. This basically absorbs the water and retards the growth of trees. It doesn't prevent it, but it slows it down, so the cables have a longer life. This, combined with water-blocking materials at the conductor shield and also at the insulation shield, creates a very long-life cable. Some of the characteristics of cross-linked polyethylene is it's a low-weight material. It's much lighter as compared to EPR, which is another common medium-voltage insulating material. It also has a very high dielectric strength, meaning that you can raise the voltage quite high before it breaks down. Another excellent characteristic of cross-linked polyethylene and tree-retardant cross-linked polyethylene is its low SIC and dissipation factor. Plainly put, these two variables together make up how lossy the insulation material is. By having a low SIC and dissipation factor, you have an insulating material that is less lossy than something with a higher SIC and dissipation factor. Also, cross-linked polyethylene is a hard material, making it very mechanically tough. EPR, on the other hand, some of its benefits are that it's very flexible as compared to cross-linked polyethylene, meaning that in installations where you have large conductors or maybe tight bends, EPR might be a better choice. It's also inherently flame retardant, or at least more flame retardant than cross-linked polyethylene. So where you have CT-rated designs, you might see EPR insulation systems. EPR is also inherently resistant to water treeing, making it ideal for submarine applications and any applications where you have extremely wet environments. And that's not to say that you can take an EPR insulation system and have no strand filling and no water-soluble powder. The more you block water out of it, the less chance you have of any problem, because any insulating material, when subjected to water and voltage stress, will tend to degrade. But EPR is inherently much better than the cross-linked polyethylene materials. EPR is also much more resistant to shrink back. This is a phenomenon that where you extrude the material and cure it, what's going to happen is the insulating material is going to start to shrink back from the conductor. With cross-linked polyethylene, you have to go back and do gradient cooling on it. In other words, you go back and heat it up and cool it slowly so that you have less shrink back. EPR doesn't have this problem inherently. As we implied before, there's a direct relationship between the magnitude of the voltage and the amount of insulation that you extrude onto the conductor. The larger the voltage or the higher the voltage, the more insulating material that you have to put on. And this assumes that you're going to have an even voltage stress around the entire circumference of the cable. Therefore, in order to obtain this, we have to have a constant potential around the outside of the circumference. Assuming that you don't have any conductive material around the circumference of the dielectric, and you lay this cable onto a ground plane, the electric field will be distorted in the direction of the ground plane. This will cause the voltage stress within the cable to be asymmetrical or unevenly distributed, meaning that one part of the cable will be subjected to a much higher voltage stress than another. If this were the case, you may as well buy egg-shaped cable, and hopefully we don't create any of that. So what we do to prevent this from happening is extrude a semiconducting material around the circumference of the cable. This is called an insulation shield, and it's a semiconducting material. By doing this, we have a conductive material around the circumference, and we have an equalized insulation stress within the dielectric. The purposes of this insulation shield, number one, is to obtain symmetrical distribution of the voltage stresses, as we said. Another one is to protect the cable connected to overhead lines or other induced potentials by providing some type of a ground path. This assumes that that's grounded, and we'll talk about that in a second. Another function of the insulation shield is to limit radio interference and also to reduce the hazard of shock. Now, as we implied before, if you have a conducting material around the circumference of the cable, the point of that is to make sure that you have that at some constant potential. Because if you don't, you'll have a potential difference between that conducting material and the ground plane. So to avoid this situation, what we do is we provide a ground, some type of a grounded conductor around the insulation shield. In this case, we're showing the standard concentric neutral shield, which is a typical URD cable. This consists of heavy copper wires, which serve multiple purposes. One of the purposes is to keep the shield, of course, at a constant potential. This can be achieved by either a fine wire shield, a copper tape shield, or a heavy wire shield, essentially any grounded conductor. In URD cables, typical utility applications, you would have a conductor that can also serve as an interceptor of system fault currents, whereas an industrial customer might have a separate ground to carry the fault currents to the ground. The utility customers generally combine this with the metallic shield, meaning that you'll have a heavy wire shield that serves as both an interceptor for fault currents and also a means of grounding that insulation shield. Another purpose of any metallic shield is to provide some type of a grounded metallic object between the energized conductor and the cable exterior. This is mostly for safety and hazard of shock. So now we've built our cable. We hopefully have a nice symmetrical distribution of voltage stress. Everything's designed as it should be. And we can put this in the ground and operate it perfectly. However, we've gone through all the trouble of making this beautiful, symmetrical, nicely shaped power cable. We want to have some means of protecting it. If we put this in a direct buried application or into a conduit where you're subjecting the cable to mechanical stresses, you could cause damage to the cable, possibly nicking the insulation, maybe distorting it, or doing something that's going to damage this beautiful cable that you've built up. So to prevent this situation, what we normally do, and we've seen this more in recent years, is have some type of a jacket over the cable. Now, electrically, this normally serves no purpose, unless it's a semiconducting jacket, in which case it can serve as a constant ground. However, assuming the jacket is insulating, you probably won't have any electrical reason for it being there. It's mostly for mechanical protection. Some of the functions, of course, is to extend the cable life. The less chance you have of damaging the cable, the longer life you have with that cable. Another function of a jacket would be to protect the cable from ultraviolet light. If you have the cables exposed to direct sunlight, you don't want those insulation shield materials to be exposed to that can cause damage. So you put a jacket on there to keep the sun from directly hitting the cable. You can also, of course, protect the cable core from physical damage during mechanical pulls. Jackets can also exclude water from the cable core. Of course, water-soluble agents beneath the jacket aid in this much more, but standard jackets, such as linear low-density polyethylene, which have basically a low moisture vapor transmission rate, can do a very good job in keeping water out of the core. Another function of some types of jackets is to add flame resistance. This is especially important in industrial applications where you have cables in cable trays. And if there's a fire, basically the cable's on a barbecue. And any flame will propagate along the length of the cable and damage more cable or equipment or personnel. Jackets also protect against neutral corrosion. Older generation unjacketed cables were put into the ground, and what they found was that the neutrals were corroding away, meaning that you don't have any grounding conductor around the insulation shield, and you certainly don't have any interceptor for system fault currents. This, of course, is an undesirable situation. So jackets can prevent the neutral corrosion and keep that grounding conductor safe and intact. There are two basic types of jackets on power cables. One is called an encapsulating jacket, and this essentially is used on concentric neutral wires, where the jacket would be extruded to fill the voids between the neutral wires. Another type of jacket would be a sleeve jacket. Taking that same scenario as a concentric neutral cable, you have some type of a separator tape, be it a water-soluble tape or maybe a mylar separator tape, and then sleeve the jacket over that so you have a smooth interface on both sides. Both have their advantages and disadvantages. Encapsulated jackets are generally a little bit better at blocking water, whereas sleeve jackets are a little bit easier in cable handling in that the cable is a little bit more flexible. But those are the two basic types of jackets. So hopefully you have a little bit of a better idea as to the different components that go into a cable design. Some of it may be a little more complex than you thought. Some of it may be a little more simple. But in any case, it's very important that you know these various components so that when you go to the field to sell these products, you don't refer to the layers as just the black thing over the pink thing. We have to understand what these different components are in order to sell the product. And if you have any questions at all, feel free to call me or any of the applications engineers, and we'll be glad to help you in trying to get these messages across to your customers. So until then, happy selling.